Now that we've imported our geometry, we're going to go ahead and make some modifications. The first modification, and I realized when I brought the PCB in, I actually brought it in with FR4, but in this case, it's a force of habit, we're going to be using a metal PCB. So it's going to use a copper substrate, so the majority of it will be copper with a 0.1 millimeter dielectric layer on top, and then traces on top of that. For this, we're actually not even going to worry about the traces on top of it because we don't know what they're going to be. So instead, we'll just model the components going directly into the dielectric layer. We'll kind of skip over that with no resistance between the component and the dielectric layer. So to start with, if we can modify the PCB, and we don't want it to be FR4, we'll just change the entire PCB and make it copper. I'm not exactly sure what copper it'll be, but we'll just use pure copper for now until we know what that is. Now I also want to add in a dielectric layer, and to do that, there's a couple ways to do it, but I think the way that I'm going to do it here is to add a 2D plane on top of it, because the PCB is already touching it. The added thickness of the copper is not going to make much of a difference. So just for the simplicity of this, if we come in to create geometry, and we call this dielectric layer, make it 2D, and then we just want to select from here to here, and then the point that we're going to. So we'll put point key planes, and that's going to be going on the closest key plane. So you can see that, and then that'll go through and update in our model where we're looking, and then pick our Y value there, and then there. Oh, okay, sorry. Make sure first that your direction is right, and in this case our direction is going to be in Y, and then come back and click it. Okay, and for the thickness, it was just 0.1 millimeters. And remember, we're in meters here. And for that, you don't have the dielectric compound, but we'll have to go through and add a new material for that, so we just call it dielectric. Hit apply. Oh, I'm not doing very well right now. Bear with me. Can't have any spaces in your names, so just use an underscore instead. And before doing anything else, come in and now I'm going to set that material property here. I'm not worried about transients, so I don't need to set these. This is set as a full insulator. Realistically, the properties are going to be a lot less than that, but in ElectroFlo, something either is a conductor or it isn't. You won't see a breakdown at a certain point of voltage of something. So if it's a conductor, it is important just for determining the Julian heating through that substance, so the I²R heating. If it's an insulator, it doesn't actually matter what properties you're using for electrical properties as long as they're greater than 1. So for our conductivity for this material, it's approximately 2. Okay. And actually, for the emissivity of it, we'll assume 0.7. I don't actually know what the, we're not doing radiation, so that doesn't actually matter, but just in case we're doing it in the future, we'll have something set there at least. Okay, so that completes the PCB now. So you have the heat into the components, has to go through the dielectric layer down into the copper board, which is then connected to the heatsink. For that heatsink, the heatsink's connected to the board. I assume there's going to be some kind of grease layer there. So to do that, we'll actually create a boundary condition of resistance and use a solid resistance. And the solid resistance is between the board and the heatsink. So if I select the heatsink and then select the board, now this means that anywhere that the board and the heatsink are in contact, and it could be that the one of the main component is within the other component, and it'll do it all around it. But anywhere these two are in contact, it's going to add an interface, and that will be relative to whatever this is. So we'll have a grease layer here, and let's just say for this analysis that the grease layer is 0.1 millimeter, and add that. And for our grease, we'll come back here and just make it 1. Okay, so there's no actual elements then for that. That's the equivalent of coming in and creating. We also have plane resistance, where you can create a resistance value in any given plane, but that's going to use that whole interface contact, and then allows you to do it in terms they generate a little easier to do. You don't have to do the little back of the envelope calculation to figure out what you want your resistance to be. Just a little shortcut. Okay, next thing is to actually set the heat in the components. So we have a chart here that shows that these components here have 10, and then a couple of them have 16 watts. Okay, and we also have a chart here, a PCB layout chart, that shows us which component is which. Just try to get this so that we can see it on the screen here. Okay, so coming back here, then that's just going to be well, BC heated volume. Now there's a couple ways to do this. I could select them from list view, so I could come up here to Model Manager and select components from here, or I could select them on the screen. So for this, I'm just going to do this, and we wanted to have everything other than D7 and D8. So I'll just select all of these and select those two, and then you can see this automatically is going to put into here, because this is going to just copy everything that is selected in your model. So you can see it selected on the screen. It's also selected here, and then we'll give that 10 watts each. Call this heated volume 10, just so that we know in the future. You could also do this individually, one by one, which would allow you to change it easier if you wanted to say, well, D3 is giving off this much, D4 is giving off this much, but just for keeping this nice and fast, we'll go ahead and do this, and then this will be 16. I'll just call this 16. Now it's per solid as opposed to total, and what that means is the 16 watts is going to go into D7 and 16 watts is going to go into D8. If you went with total, then it would be split, and the larger component would actually get more heat. So it would be split evenly based on area. It would basically change it into a volumetric property. You can also add in a volumetric property, obviously. So that's our heat done. And the next thing that we need to do is worry about the CFD. So how the model is actually going to be cooled is just going to be through CFD. At the moment, though, if we look at our mesh, it's right on the bounds, and there's no real place for the flow to grow. So we want to extend our plane. You could just create one fluid block, bring that out, but the way that I prefer to do it is to come in. Actually, let's show you how that would be done. If I wanted to create a fluid block, if you create a block out of the material fluid, that will be whatever fluid you have set in your model, and so that's in essence not there, but it will create key planes, and if you use an overwrite with that, you can actually use that to cut holes into solids. Instead, I'm going to come into Mesh, key plane edit, and user define key planes. So we're going to make some new key planes here, and I just want to extend it out both ways, and then down here, and both ways up here. So basically all around here, and then down in the Y. So let me just take care of the Y first, and we'll go to point XYZ. So this is just going to take whatever we select, click there, and you can see that automatically extends it down. That'll also automatically change our mesh. Okay, and same sort of thing here. So quickly we just make a model a little bigger here. Now we can come in and look at our mesh, and really our mesh is much smaller than it needs to be. The CFD is not going to have a great chance to grow. We have two elements between most of the fins, which will work, but preferably you'd have three elements. So if we come in and change this value and move it all the way down to say 2 millimeters, and for this, if we just say that we have 5 millimeters for our maximum, look at that, and that's much nicer, and we're still 400,000 is a very reasonable number of elements. So I'll go ahead and save this now. And so that's the CFD, the air cooling, just for natural convection. So we don't really have any other fixed temperature points. We're not going to worry about the flow on the back end. We'll just sort of leave that there because we don't know what application this is going to be in. Normally you would know the application, and maybe you have some radiation coming out the base here, or maybe you have a convection air coming over it, or there's a enclosure box on the back here. But just for this, we're just going to leave it. And majority of the heat, obviously, we have this metal PCB. 95 to 99% of the heat is all going to be coming through that board and going out these fins. So, okay, so that I think has us ready to run. I will just do a quick check here, and if we see this, we have our geometry, the heatsink, the PCB, all the components, and that dielectric layer, and then we have our BCs here, just the heated solid, and then that resistance plane for the grease.